Welcome to lecture 8. Today I will just briefly go through whatever we did in the last two lectures and give a basis for something known as transition systems for specifying the semantics of a language. So let us just briefly recapitulate what we mean by what is the framework for our operational semantics, the basic structure on which our operational semantics is to be built is the grammatical rules of the parse trees, but in a more abstract form than is really necessary for compiling. That way it's simpler, it has less number of grammatical categories which are important for meaning, and so we will take usually some form of abstract syntax trees or a representation as a context free grammar. So the important thing is that while we are talking about semantics, our context free grammar could be ambiguous, but we do not really care, because what we are interested in is only the trees where there is no ambiguity. Yeah. So let us also go through what we said about operational meaning. So our main goal is to translate or to give a meaning of a language into some form which is machine and architecture independent, and it should not be into particular machine languages or into particular architectures. It used to be the case several years ago that many languages were just defined, the meanings of the constructs were defined in terms of some abstract machine. So a machine architecture was specified and everything was specified in terms of the running of this abstract machine. But I mean, these days what we would like to do is we would like to look upon the language itself as a separate object independent of any particular machine or architecture. So we would like to give it something that is independent of these particularities. We went through the basic syntactic classes of a language, which we said were expressions, commands and declarations. These are syntactic classes which have specific meanings. So expressions, well, just denote values. There is really nothing more to expressions. Whenever we talk about an expression, its meaning is just a value evaluated in some suitable computational state. A computational state consists of an environment which gives the significance of the names used in the computation, and also maybe the notion of a store which stores values. So commands, as said, were denoted requests for irreversible changes in the state of computation, so which could mean changes either in the environment or in the store. And environments, I said, were created or changed by new declarations, and declarations are reversible and the changes in the environment are reversible. Very often declarations can also change the store, and let's just go back for a clarification on reversible and irreversible changes. So I would say that a change, so the analogy is really with something like thermodynamics. A change is irreversible not if it is impossible to undo the change, but if undoing the change requires a great deal of work or energy to be expended. Okay. Whereas a change is reversible if it requires little or no effort to undo it. So we will look upon these reversible and irreversible changes in essentially the same fashion. So very often a reversible change is one which can be undone automatically or with very little computational effort, and an irreversible change is one in which you might have to expend at least as much computational effort to undo the change as you required to make the change in the first place, right. So such changes we call irreversible. Okay, so now let us look at our specification mechanism. So since we are dealing mainly with syntax with no a priori notion of meaning, ideally what we would require, and at the background we should also remember that there are pragmatic aspects, like we should be able to implement these things at the background, but I mean that is not the most important thing. So what we will do is we will define a specification mechanism for specifying the meaning, which is essentially syntactic in nature. Okay, in the sense that it is mostly a form of symbol manipulation, symbol pushing, symbol deletions and so on and so forth, where these symbols are symbols belonging to the abstract syntax tree of the language. Okay. Since your semantics has to be firmly based on the syntax, the best way to give a meaning is in terms of the manipulation of symbols. After all, that is really all that a compiler does. So if you look at a compiler or an interpreter, it really does nothing more than that. Okay. So there are some languages whose first versions specified that the meaning of this language is exactly the compiler designed by us. Okay. So, but there are obvious pitfalls to such things. I mean, for one thing, that it is terribly source language dependent. It is terribly implementation dependent. And if the language was not implemented in some bootstrapped fashion, it is also extremely machine dependent, right. The other possibility is to just give a collection of algorithms for the various constructs of the language, but even that is too implementation specific, it is too pragmatic. It might be, for example, no collection of algorithms is complete without a collection of data structures which are manipulated. So which means that you are really designing an abstract compiler or an abstract interpreter, which is again a terribly pragmatic thing and is really of no use to most people who are going to be users rather than implementers of the language. So what is being done currently is to write a fat volume explaining the meaning of the language. So most languages really have a huge reference manual which explains the various constructs in pitiless detail, but they try to be abstract in the sense that they are not algorithmic, they are not machine specific, they are expressed in some natural language, which also has its own pitfalls. So if you look at these three methods that have been used and are currently being used, then what you find is that anything that is extremely pragmatic, like a compiler or an interpreter or a set of algorithms, has the danger that firstly it does not give the meaning of the language, because it specifies how the language is to be implemented rather than what a construct means in the language. Secondly, when we look upon meaning of a language, we regard that as an abstract mathematical object in itself. It is not necessary for it to be related to any particular method of implementation or any particular method of reasoning. Yeah. So and further, a compiler even for a small language like PL0 runs into approximately 10 pages. If the compiler were more user friendly, it would probably run to more than 20 pages of of code, of actual source language code, which makes it not too concise, because the PL0 language, for example, is a very simple language, and it's not really necessary to use the full detail of a compiler to explain the language. And so, and the important, and lastly, of course, what all this means is, all this detail means that they are all very abstract. They are not abstract enough. There are too many details which are irrelevant to a user. For example, it's too architecture specific. Maybe even if it specifies an abstract machine with an interpreter for it, it is still architecture specific. Yeah. And the main problem with these 300-page volumes that you get is that natural language is by its very nature something that was not designed but evolved, with shades and nuances of meaning. Very often these shades and nuances of meaning are geographically specific. So, and natural language is inherently ambiguous, it is too verbose, but of course the advantage it has is that it does convey a lot to a lay person. Yeah, and you can use natural language to specify the what does a construct mean, rather than how is the construct to be implemented, how is the language to be implemented. So, so currently so there is no getting away from writing a manual for the language in some natural language. Okay, I mean that's something that has to be there for a lay user, for example. But however, I mean that still does not specify the meaning of a language in an accurate fashion, right. So what we will use is something known as transition systems. Yeah. So transition systems, for one thing, they are mathematically precise, and that in itself is enough to put off a lot of people. But they have the advantage that they are sufficiently abstract. They specify the what rather than the how aspects of a language, and there are no ambiguities. And it is also an extremely concise method of specification. A layperson would probably call it too terse and completely incomprehensible maybe, but it is accurate, and what you require is something that is accurate. An accurate definition of the language is something that is required. Okay, and the other advantages of this particular method of transition systems is that it actually exploits definition by induction or definition by recursion, and it uses induction on the structure of the syntax tree to the fullest extent to specify the meaning of any construct. So what that means is that if you have a definition by induction, then you can also use the principle of mathematical induction to reason about programs in this method, right. So, and more important than anything else is the fact that actually it is not as intimidating as a layperson would think of. It is actually quite general in many ways as a specification method, because almost anything that you can think of could be expressed in terms of what are known as transition systems. Yeah. So, so for example, I mean you could and its generality goes to such an extent that very common everyday problems could also be specified as transition systems. You could specify hardware, for example, as transition systems, and actually any person who has done a hardware course has actually dealt with transition systems. The Moore machines, the Mealy machines and so on are actually transition systems of various kinds, right. And more importantly, it allows you to abstract away from details. So, you can it allows an abstraction which also is helpful in defining our equivalences. In fact, you can be so abstract if you like with your transition system definition of a language that you could take a very small detail, you could also give very detailed analysis to the extent of every step a runtime system will take, or you can go back to you can abstract away from all those details and give a larger picture which is denotational, which allows you to define equivalences, which allows you to take a purely functional view of whole programs or whole program units. Yeah. So, transition systems are really quite general in that sense, and it is a pity that it is not being taught in schools maybe. Yeah. So let's go through some elementary definitions. So, what is a transition system? A transition system is really nothing more than it is an ordered pair, it is a structure if you like, consisting of a set gamma. This is the Greek letter capital gamma, and an arrow relation, where the gamma is called the set of configurations and the arrow relation is called the transition relation. Yeah. So, this arrow is a binary relation on the configurations, and we will usually use it in an infix form. So, given two configurations gamma and gamma prime, we will say that gamma can move to gamma prime. Yeah. So, the notion of a configuration is, of course, at this point it is not being specified, but that is something we will have to specify when we actually get to the programming language. The notion of a configuration in a particular programming language will also depend upon whether, for example, it is a declarative programming language, or it is a functional language, or it is an imperative language. So, the notions of configurations will differ depending upon what kind of language it is, but largely all imperative languages will have a similar notion of configuration. All functional languages would have a similar notion of configuration. All declarative languages like logic programming languages would have a similar notion of configuration, right. And you can think about any transition system as essentially being some form of a multigraph, except that where the configurations are the nodes of the graph or the vertices of the graph, but the configurations need not be finite. Okay. And neither is the arrow relation, the transition relation, finite. So, if you can think of allowing arbitrary kinds of directed infinite graphs, and in the case of what we will call label transition systems, they might even be multigraphs. If you allow for arbitrary kinds of directed infinitary multigraphs, then you get a transition system. In fact, a directed graph can be thought of as another transition system, and your representation of Moore and Mealy machines is really in the form of directed graphs. Okay. With some special states, a special start state and a few special maybe final states, there are all these additions to the structure of a graph, but essentially it is a graph. You can look upon programs also as essentially graphs, only since programs are capable of infinite behavior, the graphs will have to be infinitary. Okay. You can look upon programs as graphs in two different ways. You can look upon programs as just trees, abstract trees, which are also graphs, but which is a purely syntactic matter. A program is a finite object in terms of its text, so the syntax tree is also a finite directed graph. The runtime behavior of a program is such that it could go through an infinite number of states. So the runtime meaning of the meaning of the program in terms of its behavior in execution could be a graph with an infinite number of nodes, but directed all the same. Yeah. So our notion of a transition system is just essentially the notion of a directed graph where we don't put any finiteness conditions on the nodes and the edges. Yeah. So just as you can have labeled graphs, that is where the edges carry labels with them, you could also define labeled transition systems. Yeah. As in the case of some of the transition systems you have already done under various other names, we can define also the set of, you can also define a terminal transition system as a transition system in which there is a subset of configurations T which are called halting configurations or terminal configurations. Yeah. So you could go further, for example, and define a labeled transition system as a labeled transition system as something that also carries labels. Yeah. So there is a collection of configurations gamma, there is a set of labels which I will call L, and there is a transition relation. Okay. So a 3 tuple in which the set of labels, there is no relationship necessarily, I mean the set of labels need not necessarily be disjoint from the set of configurations, but what happens is that corresponding to the notion of a labeled directed graph, the transition relation is a ternary relation of this form. And we would say that given a label, let us say A and two transitions gamma and gamma prime, we normally would write gamma can go on A to gamma prime. Yeah. Correspondingly, you could also define terminal labeled transition systems. Yeah. So a terminal labeled transition system would just be a 4 tuple of this form, where this is a ternary relation and T is a specified subset of gamma is a set of halting or terminal states. Yeah, so this is a terminal labeled transition system. Right? And most things, almost any kind of computational mechanism that you can think of, can be represented in some kind of a transition system, either just a transition system or a terminal transition system or a label transition system or a label terminal transition system. And how you represent it in a transition system often might depend on your viewpoint. So, we could look upon, for example, regular grammars. The fact that I said that there exists a finite state machine which recognizes the sentences of a regular grammar, that finite state machine is really nothing more than a label transition system. Yeah, you can have finite state machines with outputs, with every input which yield an output. Then all that happens is that your set of labels becomes slightly more complex. It consists of input output pairs of symbols. Yeah. So, this is a fairly general notion, and actually we think of most of our computations in the form of transition systems. How do you go from here to there, right? So, let's take a simple example. Since you already know that regular grammars are equivalent to finite state machines, what I thought was, let's give a transition system definition for context free grammars. Okay. So, here is so in general, and we can look upon it completely generally. So, we will say that, so let G be a grammar which consists of a collection of non-terminal symbols, and they are all finite, a set T of terminal symbols, a set of productions or rewrite rules or replacement rules, and a start symbol S, right. So, the set of configurations that we are talking about could just be the set of all words or the set of all strings from NUT, N union T, yeah, and the initial configuration, okay, is S, is the symbol S, and the transition relation, unfortunately the same arrow is being used for the rewrite rules and the transition relation, yeah, but let's maybe make it distinct. Should I? Okay, let's make it distinct. So, since I have written the grammar in black, the production rules I will write in black, okay. The transition system, the transition relation in the transition system, gamma arrow, is just defined as, for each production of the form A can be replaced by alpha in the production set, you have the rule that for any string, for any two strings beta and gamma, beta A gamma can become beta alpha gamma. The set of productions is finite, so the set of rules that you have is also finite, where the beta and gamma are considered completely arbitrary. So, for any particular context free grammar, this is you can just think of it as a representation of the context free grammar, in the sense that the transition system gives you this, defines exactly how your derivations should be done, defines all possible ways of deriving terminal strings, where by terminal I mean the set T of terminal symbols in the grammar. The set of configurations, the set of terminal configurations in this transition system is just the set of all possible terminal strings. Right. So, this transition system, which is written in blue, this T, the blue T here represents the fact that it is a terminal transition system of this form gamma arrow t. Yeah. So this T of the transition system is just the set of all strings in this from this T, which is the set of terminals of the context free grammar. Yeah, it is unfortunate that similar symbols are used everywhere, but I hope the color makes a difference. Okay, so essentially it's a terminal transition system, so we require these three things to be specified, and this relation is completely specified by this rule, which just says that for any beta and for any gamma, beta A gamma can go to beta alpha gamma if A replaced by alpha is a rule in the production set of this context free grammar, is a production in this set P, and if that is so, then this relation, the blue arrow, is the transition relation which gives you the set of all possible derivations in this context free grammar. So we in the case of a context free grammar, of course the symbol S has a special significance. So what it means is you can add initial states also as part of a terminal transition system. Yeah. So it depends on what kinds of details, what kinds of distinctions you have to add, but essentially the basic framework is that of transition systems. Yeah. So all these, and if you could actually go further, take your ruler compass constructions in geometry. You can look upon each ruler compass construction method itself as an algorithm, and what you are doing when you do this construction, let's take a simple problem like constructing a regular hexagon. So the method starts with taking a circle of a certain radius, choosing an arbitrary point in the circle, and with that same radius marking out the 6 vertices of the hexagon and completing the hexagon. Okay. Each of these stages is like a transition. The first step of the transition is the start state, in this case of course is a blank piece of paper, and then you move to a circle, then you move through 6 steps to marking out the potential vertices of the hexagon, and then you move through 6 steps in completing the hexagon. So they are all transitions. So you are essentially, they are the steps of an algorithm being executed. But the point is that if you look at all of these transitions as snapshots in the process, well, it just specifies what? It does not specify how. The level of detail could be so high that it might actually, the how might be implicit, but essentially it just specifies what. If I just take these, I do not know, about 15 snapshots of the construction of a regular hexagon, it just specifies what, just specify transitions. So let us take a simple programming example. So here is the towers of Hanoi problem, okay, which is I presume everybody knows the towers of Hanoi problem. You have got 3 towers and you have got some n pegs, all of different sizes, and the rules normally stated very solemnly are that all the pegs are of different sizes, and a smaller peg, a larger peg cannot sit on top of a smaller peg. Yeah, cannot. Please note the word cannot. Another rule that is stated is that if you got a pile of pegs, then you can move only the top peg. You cannot move any other peg from inside the pile, and the problem is to transform given that these are the rules, by various moves to get this set of starting from an initial configuration in which the n pegs are stored one above the other, such that smaller pegs always sit on larger pegs, to move that entire collection to another peg, to another tower, right. And so let us just quickly go through one execution of this. So here you have some initial configuration. So this these are the 3 towers, and the initial configuration is that I have just taken 3 pegs, is that you have these 3 pegs which are numbered according to their size sitting on the first tower, and the final thing is to move them all to the second tower, right. So you can go through a sequence of transitions of this form, where the next state in the transition system is that from here you can move to this, which is equivalent to saying that take the top peg in the first tower and put it on the second one, and you can move from here, which is take the top peg in the first thing and move it to the third, and well, take the peg from the middle tower and put it on the third, take the peg from the first tower and move it to the second, take the top peg from the third tower and move it to the first, take the peg from the third tower and move it to the second, and take the peg from the first tower and move it to the second. Yeah. So this is a step by step specification of an actual execution of a towers of Hanoi program, or of one possible algorithm. Yeah. So however, the question is, how do you formulate rules? For example, this execution does not tell you that you could not have moved this 3 on top of the 2 or on top of the 1. The important thing now for us is not to specify complete execution behaviors, because for example a programming language has an infinite number of possible programs and you can't specify their execution behaviors completely. So what you have to specify is rules, and you have to be able to claim that any particular execution is something that follows those rules. The productions of the context free grammar essentially are rules, or at least in our definition of the context free grammar as a transition system, they act as a hypothesis of rules which give you how derivations are performed. Okay. Note that they actually tell you how derivations are to be performed, but they do not tell you how derivations should not be performed. And there is something in the way we stated the problem of towers of Hanoi, and in the way it is stated in most books, for example, that there is this cannot. The whole business of cannot, you cannot do this, is something that is an integral part of the problem as it is stated. But in most of mathematics, nobody ever tells you what you cannot infer, they only tell you what you can infer. It is understood that you do not have a theorem of impossibility unless you can show that it is impossible with what you can do to prove that theorem. This is absolutely important. There is something in our natural language specification in which we specify what you cannot do, and what I claim is that in most of mathematics what you cannot do is never specified explicitly. Okay. So the rules of what, so we have to design rules for the towers of Hanoi problem, the specification of the problem without using these cannot. You should only specify what you can do, right. So what that means is that you could, for example, specify a rule like this. If I had a sequence of pegs, let us say S and there is some sequence S here and there is some X here, there is some T here and there is a Y on top, there is a U here and a Z on top. This X, Y and Z denote the topmost pegs. Yeah, S, T and U denote arbitrary strings in the pegs. Okay, so you could so this is perfectly fine. You can specify a rule which says that if X is less than Y, or rather if X is smaller than Y, if you like, then this peg from here can be moved on top of the Y. But you cannot specify rules like this. So here I have slashed that arrow to specify that it cannot move, right. So our natural language definition of the problem said that you cannot, for example, move a larger peg on top of a smaller peg, and this is essentially a symbolization of that. But the whole point is that you should define the rules in such a way that you do not have to do such things. After all, what you cannot do with a program is really infinite. What is finite is only what you can do with a program. Okay. So if you are going to keep specifying what all you cannot do, you have an infinite number of rules and it is not clear that you will ever proceed with execution. Yeah. So what you have to do, so our rules will always specify, except when we are informally talking about things, our rules will always specify what can be done and never what cannot be done. This is perfectly in keeping with, for example, logical inference. You don't have a rule which says that from A and B you cannot infer not A. Okay, you do not have such rules. The fact that you cannot infer not A follows from various other things. It follows from the notion of consistency or inconsistency of a logical system, of an axiomatic system. What a logical system just specifies is what you can infer and never what you cannot infer. What you cannot infer occurs as an impossibility of proof. Yeah. So this is something that we will follow also in our specification of the language. Note that pragmatically speaking also it is a nice way of specifying things. Anything that goes against what you can do is an error. It is as simple as that, right. So you generally never, there are of course certain cases in natural language where this kind of reasoning does not work. I agree with that. So very often in natural language you have to specify what you cannot do. But when we are talking about programming languages and formal objects, programs, algorithms are not very formal, but they have their representation as programs. Okay, they are all formal objects, very highly structured mathematical objects. So it is possible to get by with what you can do and assume that whatever you cannot do is something that follows as some larger consequences of what all you can do. Okay. So if I were to give rules for the towers of Hanoi as a transition system, what I will do is I will not exactly specify all the possible configurations, or I will just specify the arrow relation, the transition relation. Okay. And it is always nice to have a concise and precise set of rules and a small set of rules if possible. So what I will do is I will take an index I from 0, 1 and 2. I could be arbitrary belonging to this set, and whenever I deal with plus or minus or whatever, it is always modulo 3, right. So what I can say is and the 3 towers are actual execution specified an order for these 3 towers, the first tower, the second tower, the third tower. But the whole point is that for me now it does not matter in what order I keep these 3 towers. If I name them 0, 1 and 2, then I can use modulo 3 arithmetic to just call them SI, call them I plus 1 and I plus 2. I could take values from 0, 1 or 2, okay, with modulo 3 arithmetic. So then I can look upon the contents of the 3 towers as a set of 3 elements, and the set of all possible such sets is my set of configurations. There are specifications about what an initial configuration is and what a terminal configuration is, okay, but that goes beyond the, that is part of the problem, but it is beyond the actual notion of a transition. So regardless of what this regardless of what this I is, regardless of what order the towers are placed, I can specify this rule. The first rule says that supposing there is a, supposing the tower I, whatever may be I, is non-empty, that means it has at least one, the top token, the top peg is called A, and I plus 1 is empty. If if the tower I plus 1 is empty, then the top peg A from I can be moved to I plus 1. Yeah. Similarly, if I plus 2 is empty, the top peg A could be moved to I plus 2. Note here that we are not putting any particular, we are saying that both these are allowed, which means starting from some initial configuration it is not clear which one you are going to do. You could do either of them. For example, if you had one tower which contains all the pegs and the other 2 towers are empty, either of these rules can be applied. You can move the top peg either to one tower or to the other. So it is important to say that it's the arrow relation in a transition system does not specify what does happen or what should happen, it specifies what can happen. It does not preclude other possibilities. Yeah. So let us go through the next one. So we require this is something like a base case of an induction, okay, because you cannot compare the top element of an empty tower with the top element of a non-empty tower or something, okay. So then it is very simple. If I have, if A is less than B and B is the top element of the second tower, then A can be moved on top of B, okay. And similarly, if A is less than B and B is the top element of the first tower, then this A can be moved on top of B. Nowhere have I specified what cannot be done. These rules specify exactly what can be done, right. Given an initial configuration, you can verify that this execution that we have got actually satisfies in each transition here is an application of one of these 4 rules, okay. So that is the important thing about transition systems, it is in fact part of any kind of mathematical subject. You never specify what might be loosely called negative facts, yeah. So I hope this is convincing enough that, I mean, you can even take some purely functional program like a factorial program. The factorial program by definition is an equality, is a mathematical equality, but the unfolding of, let us say, a recursion can be regarded as a one-way rewrite rule, as a transition. So you can take the factorial program take your definition of the factorial program and go through a sequence of transitions. For any given value of n, factorial of n will go through a sequence of transitions which give you different configurations. The notion of a configuration there might be an expression itself, the unfolding of the recursion. Yeah. Okay, so we will actually start on specifying the programming language PL0 in the next class. Thank you.